All right, this is Mr. Liao, and we're doing this online. We're going to go through significance tests and talk more about p-value and what makes something statistically significant. So our objectives are to explain what statistical significance is, define the meaning of p-value, and later on use the one-sample z-test for mu and do calculations with and without a calculator, although we'll probably do that third goal in class later. So once again, the basic idea of significance test, if you forgot, is that an outcome that would rarely happen if a claim were true is good evidence that the claim is not true. So something that would rarely happen if some claim were true is strong and good evidence that the claim itself is not true. So remember the free throwing example where the guy said he was an 80% free thrower and only made 32 out of 50, and the chance of that happening was so small that either he was very unlucky or he was lying. So let's look at this idea of statistical significance. How small does the p-value need to be? Well, we can compare it to a fixed value called a significance level. We write it as the Greek letter alpha. So if we chose alpha equals 0.05, we are requiring that the data be so strong that it would happen only 5% of the time just by chance if the null hypothesis were true. If we chose an alpha of 0.01, we are requiring that the data be so strong that it would happen 1% of the time just by chance if the null hypothesis were true. So the idea is, if alpha is 0.01, our p-value, our idea of statistical significance means the p-value must be under or less than 1%. In other words, the chance of the result that we got happening was less than 1%. In fact, it was so unlikely that that gives us very strong evidence that the alternative hypothesis is true. So, how do we know if something is statistically significant? If the p-value is smaller than alpha, we say that the data are statistically significant at level alpha. In that case, we reject the null hypothesis and conclude that there is convincing evidence in favor of the alternative hypothesis. All right? So, that's what statistically significant means. It means you're trying to compare your p-value with the alpha value. Now, the alpha value you will often set on your own. And if your p-value is less than alpha, we say that the data are statistically significant. In fact, what it really means is that it is not likely to have happened strictly by chance. Okay? So if the significance level alpha makes it more exact, we might say the results were significant and p is less than 0.01, which is basically saying if the null hypothesis were true, the results that we got would have happened less than 1% of the time strictly by chance. So let's draw conclusions. We're going to let capital P represent our p-value. If we used a fixed significance level to draw a conclusion in a statistical test, if our p-value is less than alpha, we will reject the null and thus conclude that the alternative is true in context. So if p-value is below alpha, less than alpha, you reject the null. There is strong evidence against the null and strong evidence to conclude that the alternative is true. If your p-value is greater than or equal to alpha, we will fail to reject the null, and we cannot conclude that the alternative is true. So again, you do not accept the null as true. You're not trying to prove that the null is true. You're trying to prove the alternative is true. So either you do, by showing that the p-value is less than alpha, or you fail to prove the alternative is true. You fail to reject the null. You do not prove that the null is true. You don't have enough evidence to say that the null is true. You don't have enough evidence to say that the alternative is true. Remember, if the p is low, then the null must go. Again, if the p is low, then the null must go. Some of you guys might be reading that a little differently out loud, but you get the idea. Whatever helps you remember. If the p-value is low, then the null must go. It must be rejected if your p-value is low enough. So let's do some very simple p-value practice. If our alpha level is 0.05 and the p is 0.1, what do? Since our p is greater than alpha, we fail to reject the null. In number 2, alpha is 0.1, p is 0.05. Here, since our p-value is less than alpha, we reject the null. Now you can do the last 3 on your own. Feel free to stop the video and then check your answer in the next 1 minute when you're done. All right, number 3, the p-value is less than alpha. 0.001 is less than 0.01, so you will reject the null. In number 4, the p-value of 0.05 is greater than the alpha value of 0.025, so you will fail to reject the null. And finally, in number 5, your p-value is way higher than 0.1, so again, you will fail to reject the null. Again, you do not accept the null. You either reject the null and say you have enough evidence to say that the alternative is true, or if you fail to reject the null, you lack the evidence you need to state that the alternative is true. So when interpreting p-values, you will always state this. 1, you will make an explicit comparison of the p-value to the stated significance level. 2, you will state your decision about the null, whether it's rejecting the null or failing to reject the null. And number 3, you will interpret your decision in context. So when you draw a conclusion with any significance test, examiners and readers are looking for all 3 things. P-value and significance level. This is what they call linking. You want to link that p-value to your alpha value. 2, you need to make a decision on the null, whether you reject the null or fail to reject the null. And 3, you must state what that means in context. What rejecting the null means? It means you acknowledge and you have evidence to show that the alternative is true. Or if you fail to reject, you say, I don't have enough evidence to say that the alternative is true. So let's take a look at this example, better batteries. A company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. The company selects a simple random sample of 15 new batteries and uses them continuously until they are completely drained. A significance test is performed using the hypothesis where mu is the true lifetime mean of the new AAA batteries in hours. So alternative hypothesis and our null hypothesis are presented as follows. So mean, our parameter is already defined. We know what our mean is. It's the true lifetime mean of the new AAA batteries. So that is the parameter. You always want to state what the parameter is when you do a significance test. The alternative, the null hypothesis is that there is no difference. The new batteries aren't better. So the mu of these batteries lifetime is 30. Okay? It could be less than 30. We don't care if it's less. We only wonder if it's more. So the null hypothesis is that mu is equal to 30. The alternative is that the mu value is greater than 30. We want to show that these new batteries last longer than the older batteries. So a significance test is performed, and it turns out the p-value is 0.0276. All right? So, part A. What conclusion can we make at the significance level of 0.05? Well, the p-value here is less than the alpha value, so we have a statistically significant result. Since p is less than 0.05, we reject the null and have sufficient evidence to conclude that the company's deluxe AAA batteries last longer than 30 hours on average. Now notice how this is phrased. 1, you have the linkage between the p-value and the alpha value. You can even write p is less than alpha. That's fine. Secondly, you have the statement regarding the null. Here we reject the null. So that's the decision on the nulls. That's the second step. The third step you have to make is a conclusion in context. And it's basically, in this case, since you're saying that the alternative is true, you're basically stating that in your conclusion. So you have sufficient evidence to conclude that the alternative is true. That is, the company's deluxe AAA batteries last longer than 30 hours on average. So notice the conclusion has all 3 components: the linking between the p-value and alpha, the decision on the null, and the conclusion in context based on your conclusion. Now let's look at part B. What conclusion can you make at the significance level alpha equals 0.01? Well, in this case, our alpha level is not higher than the p-value. In fact, our p-value is not greater than 0.01. It's not less than 0.01. So we do not have a statistically significant result at the 1% level. So in this case, we fail to reject the null. So we link alpha is not less than 0.01. We make a decision on the null. We fail to reject. And now our conclusion. Our conclusion is that we don't have enough evidence to state the alternative is true. So in context, there is insufficient evidence that the deluxe AAA batteries last longer than 30 hours on average. So again, you don't say the evidence that the new batteries last 30 hours. No, you are trying to show that the new batteries last more than 30 hours. If you don't have enough evidence to state that, you state that we do not have enough evidence to say that the new batteries last 30 hours on average, or more than 30 hours on average. All right, there are three ways we can look at a null hypothesis versus an alternative hypothesis. And the three pictures on the slide and three pictures on your sheet. The first way is the equal versus less than test. So equal would be the null hypothesis, the less than would be the alternative. This is what's called a left tail test because you see we're looking at the area on the left tail. All right? So in this case, the null hypothesis is that the parameter equals some value or more, and the alternative is that the parameter is less than some value. So this is like the free throw percentage one. The parameter was P. P was equal to 0.8. The alternative was that the guy was poorer than an 80% free thrower. P was less than 0.8. The second type of test is called the equal hypothesis versus not equal hypothesis test. This is a two-tailed test. The null hypothesis has the parameter equaling some value, and the alternative is that the parameter does not equal some value. So this is what's called a two-tailed test because there are two tails that you could get. All right, so there are the two tails, and in this case, if the p-value falls in either of these two regions, you will reject the null. I'll get to that in a second. The third possible test is called the equal versus greater than, or the right tail test. Here, the null hypothesis is that the parameter is equal to some value, or less, and the alternative is that the parameter is greater than some value. And you see that the one tail is on the right side of the normal curve. All right? So the p-value approach is to calculate the p-value, we are looking for the area in the tails. So if you're doing a left tail test, you're looking for the area over here. For the right tail test, you're looking for the probability that you fall in one of these areas. And for two tail tests, you fall in that, you look in the middle diagram. And for the right tail test, you look at the probability that it falls in that right area. And remember, if the p-value is less than your alpha value, you will reject the null. All right, we'll stop here for now. If there's another video, I'll link to it on the School Loop page.